welcome to the course on FPGA based signal processing systems. Lecture 19 will be continuing with the sequential logic circuits, few more blocking and non-blocking assignments, examples and counter designs. So the blocking statement, in which we had taken another example here to have the better and give the better understanding. So there are three variables x, y, z, and reg G and reg B. There is another two variables which has 16 bits. So here, so the count is an integer. We see the behavioral statement. So all the behavioral statements can be fit in either initial or always blocks. So we'll be using always or initial blocks to describe the behavioral behavioral modules. So initial, begin. So we display this various the variables x, y, z. This is for the display of reg A, reg B, count x, y, z. Also the monitor task which with the time x, y, z, count reg A, reg B. So the basic the code which needs to be done here is x equal to 0, y is 1, z is 1. Now count is made 0. So what is the time at which these things, these variables get the values x 0, y 1 and z 1, count 0 on time t equal to 0. There is no delay involved in this. So assignment also can be done for the integer variable. Count is given an integer, so it integer declaration, so it will take 32 bits default. So the reg A, it's assigned 16-bit 0, that is binary, and then reg B is copied reg A. So reg B equal to reg A, so reg A will be assigned to reg B. So initializing this vector. So what we use is here x, y, z, count reg A and reg B. Let's see the hash 15 time units. This reg A of 2, that is, it is 16 bits, and the same 0, 1, 2, that is this index 2 is changed to 1 bit 1. So initialized to 0, 0, the 2 will be made to 1, index 2, and then hash 10. After that, hash 10 reg B of 13 to 15, last 3 bits will be made x, y, z. So that is x, y, z is 0, 1, 1. So the last bits will be 0, 1, 1 here after hash of 10 time units. Next is the count equal to count plus 1. Now this is just an increment end. So how this would be executed, how these statements would be executed. So see here, this is written inside the initial block, and it is getting executed sequentially, and there are blocking assignments in each. There is no non-blocking assignment. So let's see that outputs here. X equal to 0, that is that at 0th instant, and 1 at the first 0th instant itself. Y and z are getting the same values. We can see them here as well. So x, y, z 0, this is 1 and 1. Okay, these values at time, and reg A and reg B all are given. This is given 16 bits. Count is initialized to 0, and reg A and reg B are 16-bit zeros at time t equal to 0. That is initialization part we did. So after that, that is, you can see that x, y, z and reg A at 15 time units. So here 15 time units, we made it 0, 1, 2. The third bit, index 2, is made 1 in the reg A. So that is 16-bit. So you can see the code over here. So it is made 1 reg of A, that is the third bit, making 1 after 15 time units. After that, because it is executing sequentially, it is not blocking any, just any of this one. So immediate assignment. So here, next one, hash 10 after 15, after 10, after that there is 10. So x, y, z, this bits needs to be changed. So here we can very well see that at 10, after that this is at 15. After 10 time units over here, after 15, that 10 time units, that is at 25, you can see this is having the bit change of last 3 bits. okay, and this is the index change you can observe at this instant itself, and it is retained throughout remaining simulation time. So the reg B is having the last bit changed 0 1 1, okay, x is 0 y 1 1, so it's changed at 25. So you can see at 0 all of them gets initialized, at 15 the next is sequentially executing due to the blocking, at 15 that that is third bit of index 2 is getting 1 for the reg A, and next one reg B is at after 10 time units of 15, that is here 25, this is last 3 bits are getting changed. So then the count equal to count plus 1. So here till here count is 0, you can see that, and count 1 becomes 1 only after this at the 25th time unit. So though it doesn't have any time delay involved, so it is sequentially executed because of the blocking assignments. This would be executed at 25th time unit only. So 0 plus 1, it becomes 1 at this increment would be 1 here, the count becomes 1. So you can see that count 1, because it's 32 bit, it is showing that count here it's 0 and it is changing at 25th time unit. This is because of the blocking assignments. And if we continue with this, so the at time 0, this all the statements have been executed. At 15, this becomes 1. At 25, that this is copied, as well as count equal to count plus 1. So count equal to count plus 1 doesn't have any time delay, so but it is not getting executed at time t equal to 0. At 25th time units, that's the observation needs to be here, it is executed at 25 time units. Now coming this and changing them to a little bit with non-blocking and the time delay. So the non-blocking statements, so we have this XYZ and then reg A and reg B, that is 16-bit count, the same variables, and the initial part is would be the same. So to display them, so here we can have this either 0 to 0616 or simple percentage B also will work here, but to just have the 16-bit. X equal to 0, y is 1 and z is 1, count 0. Reg A is made as 0, reg B is copied with reg A at time t equal to 0. Then you can see the change over here, reg A of 2 less than or equal to non-blocking assignment hash 15 1 bit 1. Okay, so this bit select or the 1 bit needs to be replaced. This is having a 15 time delay, whereas we in the previous example we put it over here at the starting of the statement. The next one, reg B is also, this 10 is now pushed at the right hand side XYZ. So here is the hash 10. Okay, and then count less than or equal to count plus 1. You can notice the changes in the assignments. These are non-blocking assignments. Okay, now how the execution takes place. Okay, so hash 15, this is evaluated, but it is not assigned until 15. Okay, and similarly it is XYZ is evaluated, it is not assigned until hash 10, I mean 10 time units, and count equal to count plus 1 is also evaluated, and then the assignment is kept here. So let's see the outputs over here. The x is getting the value at that initialized values at the t equal to 0. Okay, now coming to reg A, that is 1, it should be changed to 1. Okay, so you can see this is getting the value at 15. That's the case with the previous blocking or non-blocking, same as that, but the evaluation and evaluated, and it is assigned only at 15. Okay, after 15 time units, this assignment has taken place, non-blocking. And then because of the delay and hash 10, next statement reg B, that is at hash 10. Okay, it's not the hash 15, after that hash 10, that is at 25. This hash 10 can see this changes in the last 3 bits, that is okay. So it's because of the non-blocking statement. And the count count, what is the count here is that it is not waiting for 25 time units. It is executed at because there is no time delay, it is evaluated, and the at time t equal to 0 it is again assigned, so it becomes 1. So then at time t equal to 0, so what is happening here, you can see the count itself is changed to 1, count equal to count plus 1, and reg A and reg B are 0 0, and remaining variables are getting assigned at time t equal to 0. And then at time at 10, that reg B, which is changing its bits 3 bits last bit, okay, that's the time the next time instant in the code, and if you use the non-blocking, and the reg A is still 0, that part select the one is which is before reg B. So it's not assigning its the left hand the evaluated value to the left hand side. The count is 1, and at 15, okay, this value gets assigned over here, reg A. Okay, so you can see the difference in this assignments, the blocking and non-blocking assignments. Okay, so 10, this is at 15, and then after 10 that was at 25. So here is the 10 itself, and count is changing at count equal to count plus 1 at time t equal to 0, because it doesn't have any time delay, whereas if you use the blocking statement, it comes with a sequential 1, and at 25th time unit in the previous example it gets incremented. So the time t, so the statements get executed is count 0 as this count also, and count equal to count plus 1 as well, and reg A, reg B is copied at 10. You see the last 3 bits of reg B is changed. At 15, then this one is made 1, that is in the third bit, that is index 2 is getting 1. So the count equal to count plus 1 is scheduled to be executed without any delay, that is time t equal to 0 itself. Okay, so whereas in the previous blocking one, it has to wait up to till 25th time unit. Okay, so you can see the difference between this blocking and non-blocking assignments. So we'll also look at the D flip-flop with 2 always blocks. Okay, so we have done with the 1 always block. Okay, so this is again the non-blocking statement as well. Input clock, the module is named as non-blocking 1, input clock, input D, and output Q and Qn T. So it has the D flip-flop has the input D and the clock, and the outputs are Q and Qn, each 1 bit. Now we have used the always block. We have just always at passage of the clock, D is assigned to Q, that is non-blocking. Okay, and you see always at the rate Q, whenever there is a change in Q, then tilde Q is assigned to Qn. Okay, this is the right way to do here, because we are not using the same variables in 2 always block. That's the condition. If you use 2 always block, though, because those are concurrent, so use D, and if you use D, or we see in the same code how it is giving the indeterminate result. Okay, so this is fine. So D is assigned to Q, and then Q tilde is calculated and assigned to Qn. Okay, so now this is whenever there is a change in Q. Okay, so if there is a change in Q, then only it gets this gets evaluated, even though there is a 2 always block. So it's a test. The test bench carries the inputs D and clock, output Q and Qn is in the case of the instantiate that in the test bench, the module or 2 always block module, DFF1B UUT, and then clock Q, also Qn, this is the instantiation. So this is the initial portion of this test bench. Then comes the displays. We use it as it in the any other example, D clock and Qn. Initialize this. This is very important to have this initialization, D clock and N. Always that we need a clock for this. So generate a clock in the test bench, has 100 clock equal to not clock. Then the stimulus. So the stimulus initial, we have this D equal to 0 for at 100 after 100 nanoseconds of time, and then D is made 1 after that it is made data is changing, keep on. So this statements we change the D, the evaluation and assign. So this is end. So these are the change in data. Can we observe that in the simulator? So the D, the clock, which is the passage of the clock, is over here, okay. Passage of the clock, what we said, D is assigned to Q, okay, yes, and then 100, this one 0 is given over here, and Qn is complemented, this is, and whenever there is a change in Q complement is assigned to Qn. D complement is assigned to Qn. That's our code, to second always block. So here passage of the clock, again this is 1 is transferred here. If there is a change in Q, then tilde of this is assigned over here. So that's Qn, that's fine. Similarly over here, that this is 0, D is 0 and passed on to this point, and whenever there is a change in Q, complement of this is assigned over here. So similar thing happen over here as well as in the Qn. So this is fine, that it works as a D flip flop without any reset. Of course, reset can be always added. So can change the, you can see the corresponding thing 100 and 100, and then there is at 300 the changes D and G. This is being copied, and 300 and 500 is being copied, at 700 it is copied, and then at 900 D is again 1. So the rest is the Q1 also can be observed here, the changes. It's fine that 2 always block works fine. So we notice that second always block doesn't have this passage of the clock. If the same code, let's see, suppose we have the DFF in 1, clock D, Q and Qn, reg declare them always at passage of the clock. Okay, what is that? D non-blocking, assign it to Q. Always at passage of the clock. You just notice the difference in the code. Instead of Q, we've taken this always at passage of the clock, assign this Q tilde to Qn. Okay, can it do that job of D flip flop? Okay, so here Q is now what would be the output? Will it be a D flip flop thing? So yes, at passage of the clock D is assigned to Q, that is fine. Okay, but will that tilde value will be proper or not? Okay, so here D is going to be assigned. So here this Q, where D is assigned to Q, and at same time passage of the clock, this Qn is demanding Q. So Q tilde. So this Q will be either the updated value or the previous value. Okay, there is a confusion over here. So it will take the previous value because this assignments didn't take place. So the Q of the previous value is complemented and assigned here. Okay, it will give the indeterminate result in this case because using the same variable with the same at the passage of the clock. Let us see that the output, this is clock, passage of the clock, passage, and the D input is changing over here. So at this point, if you see, this is 0 at passage of the clock, and it is given to Q. The first thing is over. D is assigned to non-blocking, assigned to Q, that's fine. And but Qn is at same passage of the clock, D tilde needs to be assigned to Qn. See the it is not getting the value. Okay, Qn doesn't get the value, and at next passage of the clock, yes, and here you can see next passage of the clock, this D is passed to Q, that is fine. Again at this is passed to here at passage of the clock. It works like for D1 alone, that D is passed to Q, that's fine. In Qn, what happens? So Q1 is here supposed to be 1, it is not. Okay, and here this is supposed to be 0 because this data is Q is 1, and here it should be 1, and here it should be 0, but the thing which is getting the qn is not deterministic. Okay, so what is the, so here it's fine. So the one is, it is taking the previous q which is assigned over here, okay, so 0, and making the tilde and give 1 after it. Okay, this you can observe this change. Also in this portion, it is taking that previous value 1 and making it 0, okay, and complementing it. This is 0 and complementing it. So that is here again it is taking that 1 and making it complemented. Okay, so this is the, of course this is 1, so it is matching, but that the qn is not the one which is expected. So it is giving the indeterminate result of that, but actually it should be at the same sampling edge, it should give 0, here it should be 1, and if this is 1 this should be 0, but it is giving 1. So it is taking the past value and complementing it, past value and complementing it, past value and then complementing it. So it is not updated in this code, this always block, it is not getting the q which is updated value. Okay, so it is taking the past value, and because this concurrent, these always blocks are concurrent, if you have this four this assignment, whatever the past value, and it will be assigned here, d will be assigned to q, and then the q past value will be assigned to q1, okay, like tilde and assigned to qn. So this is the qn doesn't give the proper output, it is deterministic. So coming to the counter, so this flip flops will be using in the we converted in the previous lectures d flip flop to t flip flop, either d flip flop or t flip flop or jk, any of this can be used in the synchronous counter designs. So the counter, one simple example I had taken, and then try and give the procedure to do the counters, and then we'll do the counter examples with the module Verilog module, developing the Verilog module for that in the few lectures. So counters, so we have the this is a counter of mod 4, that is 4 states. Okay, so 4 states of a 2-bit counter. This is let's assume that this counter is going to have this 0 0 as the initial state, and then it is moving to 0 1, then 1 0 and 1 1. So this counts 0 0 0 1 1 0 and 1 1. So this is the counting cycle. First we can introduce reset also, if you reset, and that should be retaining over at the same point. If not, if reset is 0, then it starts moving here with respect to the clock edge. So the input need to be, or give an input 1 which moves, which makes it move to next state, or if it is 0, go back to the previous state. All these designs can be done in the counter. So in this mod 4, the synchronous counter, actually the synchronous sequential cycles, this is have the same clock in every using all the flip flops. So here we have 4 states and 2 bits, so we'll be having 2 flip flops, right? So here we used this t flip flop. It can be even any d flip flop or jk flip flop, and so for simplicity we have taken this t flip flop, and we have also converted the d to t, and we will be using those modules to design this counter, the mod 4 counter. The state need not be 0 0 0 1 1 0 1 1, it can be in any order. So 0 0, next state can be 1 0, then you won't call it as a counter, it moves from one state to another with 2 bits of this. Okay, so in this case the present state of q0 and q1, okay, we name it as present state q0 and q1, and the next state of the counter will be with the star asterisk. So first state, suppose the present state is 0 0, so the one which we had taken here. According to our need, this next state should be 0 1, so we have made this 0 1. Okay, and if the present state is 0, then next state is 0 1. Suppose this is present state 0 1, then next state is 1 0. So this is the next state. If this is present state 1 0, and it moves to 1 1 according to this diagram. So it can be in any change. So the next state would change accordingly. And if this is present state is 1 1, and it moves to the next state is 0 0. So it counts that way. Okay. So what should be if the present state is this, and then if I move to this next state, and what should be the flip-flop input? So if I use the T flip-flop, so the present state is 0, and the next state is 0. Okay. So it is retaining that state. It is not moving, it is not changing from 0 to 1 or 1 to 0. If you use a flip-flop output, if consider this present or next state is of T flip-flop outputs, then T flip-flop output, then T flip-flop Q, then the input, the first T1 should have this input as 0. So it need not have any input to change the state. So if in the next case it is changing from 0 to 1, so it should have 1. Okay, the toggle should be there so that it is changing from 0 to 1. So in the case of third one, it is again 1 1, that there is no change in the state, so it will be 0. Okay, and for 1, the next one is 0 1 0, the state, so it is toggling, so this becomes 1. So use the excitation table to come of the T flip-flop to fill up this. Similarly, for T naught, there is another flip-flop whose input needs to be determined. So here Q naught, you take this state 0 and complement is 1. It is complementing. So T naught should be 1. So that's why it is toggling. Again here 1 to 0. Okay, 1, this is 0, toggling. Similarly 0 1, this is also toggling, and 1 to 0, this is also toggling. So the T naught counter, the counter T naught flip flop should have this all with always this is 1. Okay. So what would be next? Find the use the K map if this is only 4 states, but if you have more, and it is already we can find out what is the expression for T naught, Boolean expression required, and what is the Boolean expression for T1. So T naught, it's equal to 1 all the time, and T1 is simply if you take this one and this one, here is Q1 dash Q naught. Okay, Q1 dash Q naught, and this is 1, and here Q1 Q1 and Q naught dash. Okay, so these two cases, Q1, and then this is Q here 1 1, so Q1 Q naught, and this one case Q1 dash and Q naught. So you have in between these two things, so you have the Q naught. So you will get the expression of T1 is equal to Q naught. So for this we need to have this counter designed. So for example, take these two flip flops, the clock, and there is another flip flop with the clock. So first connect them with the same clock. Okay, Q naught and Q naught dash, and this is T1 Q1 and Q1 dash. So what is the output? This, if you interchange it, so to better view, T naught equal to 1, so you can make this 1 and simply connect this to T1. So that's output also, instead of having it's just a way of representing it there. The draw. So you have this counter, 2-bit counter, which can count up 0 0 0 1 1 0 and 1 1. So by taking these outputs, okay, so the first bit is Q naught and the second bit is Q1. Okay, this is Q naught and Q1. Okay, so this is in the order. This is 2-bit. There are 4 states. So it's a very use the excitation table and the functional table of the flip flops. Then the design can be done. Use the K map because it's only 2 bits, and we need the K map here. You can always have this K map. If you have more, suppose it's a 4-bit counter, then the map would be 4 flip flop inputs. Then so the have the variable K map will be more, so you will have 16 combinations and so on. So you have 4 variable map may be required. So if that is not in the order, okay, 0 0 1 1 1 0 1 1 0, this is in the random fashion, you want to move from one state to another, then the mod 4 counter, it can be any 4 things. So, this is the first is initially we made it 0 0, the next state is 1 1. So, we change this to next state to 1 1 instead of 0 1, and from if this is the present state 1 1 and next state is 0 1, okay, here, and if this is 0 1 in the present state and the next state is 1 0. So, just put the random states and then 1 0 and then go back to 0 0, okay. So, for this again you see the flip flop inputs how it is changing from present state, the next state is this, present state and next states are there. So, 0 and it is complemented here. So, T1 will be 1, this 1 is complemented here, yes, again this is 1 0 and it is complemented 1 and 1 is complemented 1. So, T1 becomes 1 now, okay. So, here we have this T1 equal to 1 and observe the T0 which is 0 and complemented, yes, it should be 1 and this state does not change next again. So, it is 0 and the third one changes its state, yes, toggle to be 1 and the 0 0 it is not changing, okay. So, T not equal to Q1 dash, so you will get Q1 dash. So, T0 and the T1 will be changing. So, I will just draw it over here. So, the clock and the next one is again the put the clock here. This is the clock of let us see the first bit T0 and the T1, Q0, Q0 dash, Q1, Q1 dash. So, T1 is 1 here now, T1 it is equal to 1 and the T0 is Q1 dash. So, this needs to be, I will take out this arrow mark. So, so here it should be connected. So, Q1 dash needs to be connected here. So, this will be the first bit and this is the second bit. You will get this states moving through this design, okay. So, we need to in the Verilog code we need to instantiate this T flip flops twice and make this connection also as a wire and assign this Q0 dash equal to T0, T0 would be assigned as Q0 dash, sorry, Q1 dash. Then one statement of this assign T0 equal to Q1 dash will complete the one assign statement and the 2 instantiation of the T flip flop will make it this module of the 2-bit counter. So, we have seen this 2-bit counter, that is mod 4, 4 states counter design of the synchronous counters. There are ripple counter also and we will see them the design and how to build the smallest module, what we have the D flip flop and then convert it to T flip flop and then use the T flip flop in the bigger design like in the mod 4 and then mod 4 can be extended to further larger module. These counter designs we will see in the coming lectures. Thank you.